Hello! Today we're going to be looking at graph automorphisms. So we're going to see exactly what a graph automorphism is and how we use them and how we write stuff down about them. How do we write out what we even get from them? So I'm going to look at the definition that I wrote up right here. So automorphism of a graph is a permutation sigma of the set of vertices such that two vertices x and y have an edge if and only if sigma of x and sigma of y form an edge. So that's a lot of words. What does it mean? So the way that I like to think about it is that you have a vertex, you have another vertex, and they have edges, and you're saying, okay, if I move my vertices around, if I move them to a different position, on my graph, do I still have the same number of edges? So if a vertex has one edge connecting to it, when you finish with your permutation, it still should have one edge. If it has two edges, then it should be going to two edges. So we're going to look at what that might look like with some pentagons. Let me zoom out real quick. Okay, so first thing I want to do is label my vertices so I can look at things a little bit easier. So this is going to be like the normal, if you will. So this is like how our graph usually is. This is the order our numbers are normally in. And when we find automorphisms of a graph, we look at both symmetry and rotation. So for this pentagon, we have several lines of symmetry. So we have this one coming down from 1, coming down from 2. We have 5 total lines of, oh, that one's curvy. 5 total lines of symmetry because we can cut this pentagon going from each vertex down to the line across from it. So if we were to do an automorphism, let's do the line of symmetry that goes from 1. Our 1 would stay right where it is, and our 2 would switch to 5 because it's kind of like we're flipping it over. Our 3 would go to 4, our 4 would go to 3, and our 2 would go to the 5 spot. So when we write this, we can write this in something called cyclic notation, and that just tells us what changes we did and where our numbers are going to go now. So when we do this, we normally write like maybe a 1, which this part is optional because 1 didn't move, and then we'd have like, okay, 2 goes to 5, which then goes back to 2. See, it's a cycle because it goes in the circle. Okay, and then we'd also have 3 going to 4. And so this is how you'd write out this automorphism. And so you're just writing out the changes that happen. But we can also do rotation. So we're going to see what happens when we rotate just one spot over, and everything else is going to follow in the same way. So we'd put 1 over here, 2 would go down here. Oh no, I can't see. Okay. 3 would go over here, 4 would go over here, and 5 would go over here. So the way we write this one is we say, okay, our 1 is going to our 2 spot. Our 2 is going to our 3 spot. 3 is going to the 4 spot, and 4 is going to the 5 spot. Now this one up here, since nothing's changing, we often write this as just an open parentheses with nothing in it because nothing changed. Everything is just exactly where it was before. So another thing with the rotations, if we did something a little different, I'm not going to draw it again because it won't look like the pentagon, but if we made 1 go here, that would be saying, okay, 1 goes to our 3 spot, 3 is moving 2, so it's going to the 5 spot, 5 is moving 2, which means it's going to our 2 spot, and then our 2 is going to our 4 spot, which then goes back to 1. So in this one we have 5 symmetries, and then we also have 5 rotations, which makes for 10 total automorphisms. And I didn't think we would run through all of them right now, but if you were curious what the other ones are, here it is right here. And we looked at, I believe, this one, this one, this one, and this one. And I think if you looked at it, you could figure the rest of them out. We're also going to look at these 2 graphs and kind of look at what happens when we have vertices that only have one edge connecting to them. And I know my lines are kind of wonky on this one, so just ignore that fact. So for this one, first we're going to say, okay, what can move on our graph? Well, this 4 doesn't have any other edges, and none of the other points have no edges. So that means that this 4 is always staying where it is. The 1 and the 3 both have one edge, whoop, whoop, and right there. So that means 1 and 3 can swap with each other. And then 2 has to stay also because it has 2 edges, and none of the other ones have 2 edges. So this is an automorphism of a graph, and then just the normal automorphism. And that's actually the only 2 that we have for this one, because 1 and 3 are the only ones that can swap. So for this one over here, we have 2 edges on each of them, which means that all of them can switch with each other. So I know I didn't draw an equilateral triangle, but let's pretend that it's an equilateral triangle. So if that's the case, then we have 3 lines of symmetry that we can go with. So with these 3 lines of symmetry, we could say, okay, 1 is going to 3, that's it. Or for this one, we could say, okay, 2 is going to 3, which goes back to 2, and that's it. Or we could say 1 is going to 2, and that's it. We also have our normal one, which is just the original. And then we have 3 different rotations we can do, where we go 1 goes to 2, which goes to 3. 1 goes to 3, which goes to 2. Oh my goodness. And let's see. I think that's it. Yeah, so we just have 6 automorphisms for this graph. And that's all I have to show you today. But I hope it has increased your understanding of graph automorphisms.